علیکم. پچھلے لیکچر میں ہم سافٹ ویئر ٹیسٹنگ اسٹریٹجی کے اوپر بات کر رہے تھے. ہم نے ڈسکس کیے تھے اسٹریٹجک ایشوز اور کریکٹرسٹکس جو اسٹریٹجی کا حصہ ہوتے ہیں, اور پھر ہم نے ڈیٹیل سے بات کی تھی یونٹ ٹیسٹنگ کے اوپر اور انٹیگریشن ٹیسٹنگ کے اوپر. یہاں میں ایک دفعہ پھر ریویو کرنا چاہتا ہوں. یونٹ ٹیسٹنگ کے جو ٹیکنیکس ہیں وہ یوزلی بلکہ وائٹ باکس ٹیکنیکس یوز ہوتی ہیں, جبکہ انٹیگریشن ٹیسٹنگ میں اکثر بلیک باکس ٹیکنیکس یوز ہوتی ہیں. انٹیگریشن جو ہے وہ بہت امپورٹنٹ کرٹیکل ایسپیکٹ ہے سافٹ ویئر ڈیولپمنٹ ایکٹیویٹی کا, کیونکہ اس وقت وہ تمام انڈیویجول کمپوننٹس جو ہم نے ڈیولپ کیے ہوتے ہیں, ان کو ہم نے ٹیسٹ کیا ہوتا ہے, ان کو ہم کمبائن کر کے مختلف اپروچز کے ساتھ کمبائن کر کے ایک پروڈکٹ بناتے ہیں. تو انٹیگریشن ٹیسٹنگ کی مختلف اپروچز ہیں, جس میں ٹاپ ڈاؤن انٹیگریشن ہے, باٹم اپ انٹیگریشن ہے, یا ان دو کو کمبائن کر کے سینڈوچ اپروچ بھی ایک بنائی گئی ہے. اور میں نے ذکر کیا تھا کہ سافٹ ویئر ٹیسٹنگ میں انٹیگریشن کے حوالے سے کافی ریسرچ ہوئی ہے, اور یہ ایک ایسا ایریا ہے جس میں اگر ہم بہتری لا سکیں تو سافٹ ویئر کو جو سافٹ ویئر پروڈکٹ ہے اس کو پٹ ٹوگیدر کرنے میں, اس کو انٹیگریٹ کرنے میں بہت مدد مل سکتی ہے. تو اسی ڈسکشن کو ہم لے کر آج چلیں گے, اور آج ہم سافٹ ویئر ٹیسٹنگ اسٹریٹجی کا ایک اور امپورٹنٹ ایلیمنٹ ہے ویلیڈیشن ٹیسٹنگ, اس کے اوپر بات کریں گے, یعنی اس سے ہم لیکچر کا آغاز کریں گے. اور ایک اور ایلیمنٹ ہے جس کا ہم نے اسٹریٹجی کو ڈسکس کرتے ہوئے شروع میں ذکر کیا تھا, اور وہ ہے ڈی بگنگ. ڈی بگنگ از یوزلی ناٹ ٹیسٹنگ, بٹ اٹ فالوز after testing. This is an act where we actually find the defect and remove it from the software code. اس کے اوپر بھی ہم آج کافی بات کریں گے. So let's begin our discussion on validation testing. Validation کیا چیز ہے؟ ویلیڈیشن یہ ہے کہ کسی چیز کو ویلیڈیٹ کیا جائے. ہم چونکہ سافٹ ویئر پروڈکٹس کی بات کر رہے ہیں تو ہم کہتے ہیں کہ سافٹ ویئر پروڈکٹ اس وقت ویلیڈیٹ ہو سکتی ہے یا ہو جاتی ہے جب اس کی فنکشنالٹی, اس پروڈکٹ میں وہ فنکشنالٹی ہو جو اس میں ہونی چاہیے. In other words, we can say that validation succeeds when software functions or operates in a manner that can be reasonably expected by the customer. And it is achieved through a series of black box tests that demonstrate conformity to requirements. آپ کو میں نے وی ماڈل دکھایا تھا of software testing, and in that model we developed the relationship between requirements and validation testing. So if we want to successfully execute and conduct validation testing activity, we must have access to all the requirement set. We must have access to the requirements model, and we must have done preparation and planning based on that requirements set to perform validation test. اگر ہم نے یہ کام نہیں کیا, یعنی کہ ہم نے ریکوائرمنٹس ماڈل کو یوز نہیں کیا ویلیڈیشن ٹیسٹنگ کے لیے, تو ہماری ویلیڈیشن ٹیسٹنگ جو ہوگی وہ ایڈ ہاک ویلیڈیشن ٹیسٹنگ. وی ول ناٹ بی شیور آف ایگزیکٹلی واٹ ہیز بین ڈن اینڈ واٹ ہیز بین اچیوڈ. تو سافٹ ویئر ٹیسٹنگ, لائک اینی ادر سافٹ ویئر انجینئرنگ ایکٹیویٹی, نیڈس ٹو بی planned and executed in a systematic way. And the test plan outlines the classes of tests to be conducted, and test procedures defines the specific test cases that will be used to demonstrate the conformity to requirements. So this is not an ad hoc activity. I have to convey this very forcefully and very convincingly, that software testing should not be taken as an ad hoc activity. It requires planning, it requires preparation, and it requires proactive participation on part of all those who are involved in any testing activity, whether that's planning or whether that's preparation of test cases or whether that's actually execution of the test procedure. And so we should give proper and adequate time and allocate necessary resources to perform all kinds of testing, whether that's unit testing or integration testing or validation testing. At this time, we are talking about validation testing. And when we are talking about validation testing, we have to ensure that both the test plan and the procedures are designed so that we ensure that all requirements are met, that all behavioral characteristics are achieved, that all performance requirements are attained, that the documentation is correct, and that human engineered and other requirements are met. So this is a very complex and detailed task. The test planners have to study the requirements document very thoroughly so that they can generate the test cases necessary to test all the requirements and to look at all the and to check the conformity of all the non-functional requirements in particular. Because typically most of the functional requirements are implemented in a software product, and sometimes the proper care or attention is not given to non-functional requirement. And so it is the responsibility of those professionals who are charged to develop test cases for validation testing to ensure that all the non-functional characteristics, all the non-functional requirements of the intended software product are actually tested in the product that they are given, and that they need to have a plan for it, and they need to define the procedures on how they are actually going to execute that test plan. After a validation test case has been conducted, there are two possibilities. One is that the function or performance of the characteristics conform to the requirements and are acceptable to the customer as stated in the requirements model. And number two, the deviation from specification is uncovered, and as a result you need to create a deficiency list. This deviation means that a particular requirement, whether that's a functional requirement or a non-functional requirement, has not been implemented in the software product as was desired. And so it is the responsibility of the people who are conducting validation tests to record that information and to create what is described as a deficiency list. The problem that usually happens is that if you discover a deficiency at validation time, it would be too late to actually repair that defect or to fix that deficiency or to remove that deficiency. Because as you know, that validation testing is usually one of the last activities before the software product is handled or is passed on to the customer, is given to the customer. And so the customer needs to be informed, and it would become necessary to negotiate with the customer to establish a method for resolving deficiencies found at the validation time. And at this time, the customer may choose to delay the delivery of the product, and the development team can then go and fix the deficiency, or they may accept the product with the understanding, or maybe in a written fashion, written contract may have to be developed so that they are given the product as is, and the developer would then have to go and update the product later on after removing the deficiency. But certainly the customer has to be involved, and I can assure you that there will be embarrassment on part of the development team that they were not able to deliver the product without defects at the expected date. Validation testing is a form of high order testing, and typically for software engineering projects, this is the last form of higher order testing, although there are other higher order testing activities also that include acceptance testing. Some projects require alpha testing, which is also another high order testing. Alpha testing typically is performed at the developer site by the customer. Then there is beta testing, which is another form of high order testing approaches, and this is performed at the customer site without the developer's presence. And a lot of commercial software products release their beta versions, and prospective customers use those beta versions to test the new software product, and they do it typically in their own sites. And then there's a systems testing, which we had talked about a little bit in the last lecture also. And system testing involves testing software with hardware, with people, and with databases, and typically it involves a system engineering project. The scope of system testing for software engineering project is quite a bit less as compared to system engineering projects. There are certain other specialized forms of testing also, and depending on the nature of the project, these specialized forms of testing may have to be included in our testing strategy. I will briefly describe what these specialized testing approaches are. First one is recovery testing. This would, as the name suggests, deals with the recovery of the software services and software products. When the software systems go down for one reason or the other, and once they recover from their crash, certain testing has to be performed. This type of software testing is not done for ordinary software projects, but it is performed for certain real-time systems where full recovery and for those hardware-based machines, hardware-based systems where software is running the entire operations, and so complete recovery of the entire system is important. Then we have security testing. Increasingly, software services are being provided over the web, and even if the services are not being provided over the web, intranets within the company and client server software applications within an organization require that they go through security testing. Increasingly, software is being threatened by defects or bugs which come in the form of security holes, which come in the form of areas in which security is lax, and as a result viruses and other infections creep into the software products and make the softwares useless and damage the computer systems, and as a result the organizations suffer both in terms of loss of time and in terms of loss of money. And there are so many problems that security testing, though a specialized form of testing, is increasingly becoming a standard part of the testing strategy. In fact, if you are dealing with web-based systems, security testing has to be part of any strategy that you develop to test the software systems. Then there is stress testing. It deals with the number of current users. For example, if you are developing a website, every website has a minimum load requirement, and stress testing is a way to check if the website can handle that load. Similarly, even for non-web applications, stress testing is an important part. If the number of users using the software system concurrently is high. There are other issues with it, usage of specific databases and operating system constraints, but again, stress testing is an important part in overall testing strategy. Similarly, there are certain operating conditions which require us to perform stress testing. There is a specialized form of stress testing known as sensitivity testing, which also deals with more sensitive issues of stress testing. Then there is performance testing for those software systems which require that they provide service according to certain performance requirements, and these requirements are then documented in the requirements model. Then performance testing needs to be conducted. This form of testing, although efficiency and effectiveness is important for all software systems, but certain software applications are performance oriented, and they require that the users be given the responses in such a way that performance is measured as a quantifiable metric and is documented as such in the requirements model. So performance testing again is a very important part of software testing strategy, and it has two parts. One deals with the software, performance of software, and the other is the performance of the network, and both of them coupled will actually be tested if we conduct performance testing. We had talked about testing strategies and testing techniques and the role of software testing in quality assurance. Now I'm going to show you a table which relates software testing and litigation as a result of poor software quality. So as you can see on this table, that there are certain characteristics of reliable software, and there are certain negative aspects of software products which are involved in litigation because of poor quality software and because of poor quality. And so you can see that and I'm only going to highlight areas where improvement is needed. So if you look at new function testing and regression testing and system testing, performance testing, and capacity testing, which is another form of stress testing, that these activities were either rushed or omitted in those software products which had poor quality, and the development organization was taken to court of law because of their poor quality and because they did not meet the necessary contractual requirements as far as the quality of software was concerned. So this table highlights the importance of conducting all the necessary testing activities, whether they are for small or low-level units or for larger software product as a whole. And so we need to perform software testing in the small as well as small software testing in the large. We need to apply white box testing techniques and black box testing techniques based on the need of the product, based on the contractual agreement, based on the criticality of the software product. And if you look at the testing performed for reliable software systems, you see that all the necessary testing activities were performed. So this table gives us a clear indication of the importance of using different software testing approaches and to include the necessary approaches and techniques in the testing strategy for a product. This completes our discussion on validation testing. Now we will proceed to another very important aspect that comes after software testing, and that is debugging. We must plan and execute our testing activities in a systematic manner. And after the completion of the testing activity, and based on the test plan and test strategy, we would have to conduct what is known as the process of debugging. Debugging, as I have said, occurs as a consequence of successful testing. You know that successful testing results in the identification of software defects. Or we can say that successful testing results in the observation of failure of software. So when a test case uncovers an error, we need to perform the debugging process, or we need to execute the debugging process. This is the debugging process that removes the error from the software code. It is not testing which removes the defect or bug from the software code. Testing only results in the observation of failure, and then this observation is taken and used as an indication to, number one, first find the defect, and then to remove the defect. we can say that debugging is an art. It's an art because of the reasons we will talk about a little later. But one thing is that we have to execute this process of debugging every time we run a successful software test. The test will give symptoms or indications of software problems. The external manifestation of the error and the internal cause of the error may have no obvious relationship to one another. And so what I'm saying is that testing is going to, or successful testing is going to result in the symptoms of an error. It is the responsibility of the assigned personnel to take those symptoms and find the actual cause of error. That process is debugging process, and there is no scientific approach to carry out that process, although there are techniques, but still this is a poorly understood mental process which connects the symptoms to the cause, and this connection from symptom to cause is the debugging process, and that is why it is more close to being called as art of debugging as compared to science of debugging. Debugging, as I said, is not testing, but it always occurs as a consequence of software testing, actually successful software testing. Now I'm going to show you the debugging process. Here you have on the screen a debugging process where you have test cases which were used by the tester. The tests were executed, the results were produced and recorded, and the process of debugging starts as a result of the execution of successful tests. Now, once the successful test results in the failure of observation, that information is given to software engineers who would then find the causes of failure and remove them from the programs. So we can say that the debugging process begins with the execution of a test case, results are assessed, and a lack of correspondence between expected and actual performance is encountered. That is, you have observed a failure. In many cases, the non-correspondence data are a symptom of an underlying cause as yet hidden. We don't know as to the reason why these results are produced, and there is no obvious link between the symptoms and the actual cause of the failure. The debugging process attempts to match the symptom with the cause, thereby leading to error correction. So as I said, that this is a process which is not fully understood, and that is why we call it the art of debugging. Now, the debugging process will always have one of two outcomes. One is that the cause will be identified. If the cause is identified, then we remove the cause, and as a result, the software will be corrected. And the second case, the second outcome, that the cause is not found, is a little bit alarming. In that case, the person who is performing the debugging may suspect a cause, and if that is the case, then he or she would have to generate new test cases and find the cause of the failure in an iterative fashion. But one thing is clear, and that is we cannot proceed without finding the cause which is resulting in the failure of software or the success of software testing. Now I'm going to show you a picture which will depict the debugging process from the debugger's perspective. So the picture is titled Debugging Effort. So the effort is spent in primarily two things. One is time required to diagnose the symptom and determine the cause, and second is time required to correct the error and conduct the regression tests, and both of these are circularly attached to each other and one follows the other. And so the entire time spent in the debugging effort can be pictorially shown here. So you have seen the picture of debugging effort, and you can imagine and understand that this is a human-oriented process. Some people are good at debugging while others are not. And if you look at the literature, large variances are reported in debugging ability for programmers with the same education and experience. And so it is an ability that some professionals develop and enhance as part of their growth in the profession, while others lack in this area. I'm going to now share with you a very interesting quotation from Schneiderman, who says that debugging is one of the more frustrating parts of programming. It has elements of problem solving or brain teasers, coupled with the annoying recognition that you have made a mistake. Heightened anxiety and unwillingness to accept the possibility of errors increases the task difficulty. Fortunately, there is a great sigh of relief and a lessening of tension when the bug is ultimately corrected. So this quotation is a very good representation of the process of debugging and how programmers feel about it. There is another aspect of it, and that is much time spent there's another aspect of it, and that is the programmers spend quite a bit of their time throughout their professional life in the process of debugging, because they make mistakes. Those mistakes are then either caught in inspections, or if they're not caught in inspections, they're caught in software testing, and the process of debugging starts. So this is a realization that all programming professionals have to deal with once they join this profession, that their time, quite a bit of their time, is spent in the process of debugging. Now let's talk a little bit about characteristics of bugs and defects, because understanding these characteristics is also useful in the process of debugging. Number one, the symptom and cause may be geographically remote. That is, the symptom may appear in one part of the program, while the cause may actually be located at a site that is far removed. Highly coupled program structures exasperate this situation. And so going back to our concepts of software design and development, we said that rules coupling is good. It's good for design, it's good for programming. Here we know it's good for testing also. Second is that symptom may disappear temporarily when another error is created. So that is also an interesting characteristic that helps us in the process of debugging. Knowing this helps us in the process of debugging. The symptom may actually be caused by non-errors, for example, like rounding off inaccuracies. And in those systems, in those applications where precise, accurate numbers are required, especially floating point, this can be a situation. The symptom may be caused by human error, and I can assure you that human errors cannot be traced easily. The symptom may be a result of a timing problem rather than a processing problem, so that this is particularly true for real-time systems, and timing constraints and sequencing issues also can cause certain defects. Then another characteristic is that it may be difficult to accurately reproduce input conditions. For example, in a real-time system application, it may be difficult to recreate input ordering as the one which caused the symptom, that is the one which caused the failure in the software system. And so, knowing this helps you in the process of debugging so that you can have better test cases. The symptom may be intermittent. This is particularly common in embedded systems that couple hardware and software inextricably, and it is sometimes possible that the error is not generated by a software piece of code, but it may be because of some hardware malfunction. The eighth is that the system may be due to causes that are distributed across a number of tasks running on different processors. So if you have multi-processor environment and they are sharing their information through different software techniques, then that may be good to know for the process of debugging. And I tell you that as the systems become more complex, we have multi-processor environments, we have parallel processing, we have concurrent processing, and we have other constraints. The process of debugging becomes difficult every day. So the process of debugging is not a scientific process. It requires problem-solving skills. It requires enhanced and practiced ability to relate the symptoms to causes, and it also requires that you have good domain knowledge, because if you have good domain knowledge, you will be able to relate the symptoms with the causes fairly quickly. Now I'm going to show you a picture which captures which describes the consequences of bugs or defects. Here you have on the x-axis a defect type or bug type, and on the y-axis the damage that's done. So you have mild, annoying defects and disturbing, some serious defects, some extreme defects, and some catastrophic defects. And on the top of the list is the infections that I was talking a little bit earlier when I was discussing security testing. And the bug categories can be function-related bugs, system-related bugs, data bugs, coding bugs, design bugs, documentation bugs, standards violation, etc. But if you look at this chart, you will notice that the most damage done is usually done by the infections that come from outside and destroy your security systems. So it is important that we execute our debugging process in a fashion that we can relate the symptoms with causes, and we need to acquire the necessary knowledge and skills to do that. There are a number of debugging approaches, and it doesn't matter which approach you choose to select for one project. There is simply one objective, and that is to find and correct the cause of the software error. This objective is realized by a combination of systematic evaluation, intuition, and luck. So you have three things. You have systematic evaluation, so you need to execute the process of debugging systematically. You should develop intuition, and you may be lucky in developing the relationship between symptom and cause, but this luck has to do with your hard work. Debugging approaches include brute force approach, backtracking, and cause elimination, and we will talk about these now. The brute force debugging approach is probably the most common and least efficient method for isolating the cause of a software error. Most students use this, and many young professionals use this also. We apply brute force debugging methods when all else fails. And we can have the mantra, let the computer find the errors. We take memory dumps, we take runtime traces, and we fill our programs, we load our programs with lot of write statements, lot of output statements, output messages that indicate the sort of tracing as to where we are and what the value of different variables and data structures is at a given time. And we hope that somewhere in this morass of information that is produced, we will find a clue that can lead us to the cause of an error. And so this is all ad hoc approach in trying to find a cause of a failure. Although the mass of information produced may ultimately lead to success, and most of them do, it more frequently leads to wasted effort and time. A lot of time and effort is required to apply and to use the brute force debugging. So how you should avoid that? You should think about it. You should try to think about possible causes when certain symptoms are injected or certain symptoms are shown by the system. So we say that thought must be expended first. Instead of spending time and effort, spend or expend your thoughts. Develop possible scenarios that this might have happened because these symptoms are shown. These symptoms might have been as a result of this reason or that reason. And that way you can eliminate a lot of causes, as we will see later. So the second approach that we talked about was backtrack debugging or backtracking debugging. Backtracking is a fairly common debugging approach that can be used successfully in small programs. Beginning at the site where the symptom has been uncovered or reported, the source code is traced backward, and that has to be done manually until the site that the cause is found. So this requires that once the symptom has been shown, you manually go back and check different values and try to find the cause. But this can only be applied to small pieces of software code. because as the number of source lines increase, that is, the size of the software code increases, the number of potential backward paths may become unmanageably large. So for small units, this technique or this approach may work. Then we have cause elimination debugging. Cause elimination is manifested by induction or deduction and introduces the concept of binary partitioning. Data related to error occurrences are organized to isolate potential causes. This is what I was talking about when I said that thought must be expended first, that you need to try to eliminate certain causes based on the information that has become known to you by the symptoms. So you need to develop what is known as the cause hypothesis, and you need to devise that based on the data that's available to you to prove or disprove the hypothesis. And so that way you can reach the cause of failure in shorter time as compared to brute force approach. You can also alternatively list all possible causes and develop tests, conduct those tests to test whether that cause is the reason for failure. And so we use the process of elimination. If certain causes show promise, then we can refine the data for test cases also. And so by using cause elimination debugging, we can perform better compared to the backtracking or brute force debugging approaches. Now, once a defect or a bug has been found, it must be corrected. That's the reason why we are performing this activity. We also know that when we are fixing defects, we can introduce new defects or new bugs in the software. So we need to ask 3 questions before we fix a bug. Number 1, is the cause of bug reproduced in another part of the program? इसका मतलब यह है कि क्या जो ये cause है ये कहीं और भी किसी और प्रोग्राम के किसी और हिस्से में भी है? अगर है तो हमें वहाँ पर भी दुरुस्ती करनी पड़ेगी. Number 2, what next bug might be introduced by the fix I'm going to make? यानी कि जो मैं डिफेक्ट्स दूर कर रहा हूँ उसके नतीजा में कोई नया डिफेक्ट तो नहीं आ जाएगा. And number 3, what could we have done to prevent this bug in the first place? इसका ये मतलब है कि क्या हम एक्शंस कर सकते थे या क्या प्रिवेंशन एक्टिविटी होनी चाहिए थी जिससे ये डिफेक्ट यहाँ पर ना आता, पहली दफ़ा में ही हम इसको इंट्रोड्यूस ही ना करते. और इन तीनों सवालों के जवाब लेकर हम वो डिफेक्ट जो है वो उसको रिमूव कर दें, उसकी रिपेयर कर दें, और अगर कहीं और भी उसके नतीजे में रिपेयर्स होनी है तो उनको भी करके एंड वी परफॉर्म रिग्रेशन टेस्टिंग so that we ensure that the fixes that we have performed, the bugs that we have removed, have not introduced new defects in the software product. तो आज के लेक्चर में हमने वैलिडेशन टेस्टिंग के ऊपर बात की थी और उसके बाद हमने डीबगिंग प्रोसेस के ऊपर काफ़ी डिटेल से बात की है. नेक्स्ट लेक्चर में हम एक और टॉपिक के ऊपर बात करेंगे. टिल देन I take leave of you. Allah Hafiz.